In this video, we'll be going through the easy questions on the Young modulus. The first question is asking for a definition of tensile stress and tensile strain. Tensile just means you're pulling something apart rather than compressive, where you're pushing something together. So tensile stress is the force exerted per unit cross-sectional area of a material, and I've written the equation there as well. Stress, which we measure in pascals or newtons per metre squared, is equal to the force in newtons divided by the area. And then strain is the extension per unit length. And to work out strain, you do the change in length, or the extension, divided by the original length. Question 1b, we have a stress-strain graph for a wire up until it fractures, and we need to determine the breaking stress of this copper wire. So this is where the wire breaks, where it fractures. So I've drawn a line from the fracture point over to my y-axis where the stress is, and it hits at 1.9. But if you spot here, the stress is in 10 to the power of 8 pascals. So our answer is 1.9 times 10 to the 8 pascals. Unfortunately, you wouldn't get the mark if you forgot the times 10 to the 8. So always make sure you're checking for your units in your labels on your axes. The next question wants us to work out the Young's modulus of this. So I've drawn on some lines. You can work out the Young's modulus by working out the gradient anywhere where the graph is still a straight line. So don't do it when it curves, but just before it curves. So I've drawn lines here. So it's at 1.04 times 10 to the 8 for our stress and 0.9 for our strain. And then I will put them in our equation, stress divided by strain. And when you divide it, you get a Young's modulus of 1.16 times 10 to the 11, and we've got to give a unit, so pascals, or you can always put newtons per metre squared as well. Question 1d is talking about a new material with a Young's modulus less than copper, and that undergoes a brittle fracture at a stress of 176 megapascals. Draw a line showing what this could look like. So if we draw it on the graph, it is brittle, so we know it's not going to have plastic deformation at the end, it's not going to curve very much, and it has a lower Young's modulus, so the line is going to be slightly more shallow. So I've done a little point on my y-axis where 1.76 would be, or 176 megapascals, so that's where it's going to end, and I'm just going to draw a straight line with a lower gradient to around that point, and then it's going to have a little fracture at the end. So as long as it's less steep, it's more shallow, it will be correct. So there's an example, and I've curved it just slightly at the end to show that it's broken, but it goes up to 1.76 and it's a brittle break at the end there. Question 2a is asking for a definition of the Young modulus. So in words, it's the ratio of tensile stress to tensile strain, but we're more likely to see it as an equation. So the capital E is for our Young's modulus. This symbol here, a sigma, is for stress, and this is for strain. Question 2b has given us a wire with a diameter of 2 millimeters, and we need to calculate the area. So because it's a wire, it's going to be a circle like this, and it's given us the diameter like that. So there's a few different ways you can do it. So the equation for area is pi r squared, but we can also change that to have d the diameter, which is pi d squared over 4, or you might have seen it written d over 2, and that's squared. All of these will work, but I've also noticed that the 2 is in millimeters and it wants it in meters squared, so we're going to need to convert it. So what I'm going to type into my calculator is pi 2 times 10 to the negative 3 for our millimeters. That's going to be squared, and then I'm going to divide it by 4. And the answer you should get is 3.14 times 10 to the negative 6 meters squared. Question 2c, we've been given a force of 15 newtons, so tensile again means just that we're stretching it, and we need to work out whatever the stress is, and from above we have the area, 3.14 times 10 to the negative 6. So what we're going to do is we're going to use our equation for stress, which is force divided by area. So we're going to do 15 divided by 3.14 times 10 to the negative 6. And the answer you should get is 4.8 times 10 to the 6 pascals. Or we could also write Newton per meters squared. And that is rounded to two significant figures. Our next question is linking our Young's modulus that it's given us, 120 gigapascals, the stress that we worked out last question, and it wants us to calculate the strain. The reason it's given us this 15 newtons is just to say the stress that we calculated in our last question is still correct. So we're going to be rearranging this equation, stress divided by strain. So strain is stress divided by the Young's modulus. So our stress, we can use what we got from our last question. I've written it out before rounding, and we're going to divide it by our Young's modulus, which is 120 gigapascals, which means times 10 to the power of 9. So we type that into our calculator, and what you should get for your strain is 3.982 times 10 to the negative 5, and there's no unit for strain, but we will round that to 4.0 times 10 to the negative 5 to a convenient number of significant figures. 3a is talking about an experiment that we could use to calculate the Young's modulus of a wire, label it to show how they could use it. So first of all, on the left we've got our G-clamp. This clamps everything to the bench to make sure it doesn't slip. We then have the end of a wire clamped between two wooden blocks. Here's our wire, and then we've got a ruler to measure the extension, and we've got a marker to help us mark the extension. There are two different ways we could calculate extension. One of them uses a marker. We've got a pulley, which is what our wire is attached to, or our wire goes over, and then we've got some weights to make our wire extend. Question 3b is about considering the safety considerations when we carry out the experiment. So there was two safety things that I could think of. First one is to wear safety goggles in case the wire snaps, and the second one is to place a soft surface underneath the mass hangers in case they fall off. Question 3c asks us to draw a graph to show the relationship between stress and strain that they would obtain, as long as it is not stretched beyond the limit of proportionality. So until it reaches that limit, we should get a straight line that goes through 0, through the origin here. That shows that it obeys Hooke's law and that stress is proportional to strain. 3d, state how Young's modulus value could be obtained from the graph. So all you would do is calculate the gradient of the line, so that's the change in y divided by the change in x. And that's because our Young's modulus is equal to stress divided by strain. Question 4a wants us to calculate the Young's modulus of a fishing line. So we have got the stress of 20 megapascals and the strain of 3 times 10 to the negative 2, no unit for strain. So we are going to use the equation stress divided by strain. Usually I would get rid of the megapascals and just turn it into pascals, but it wants our answer in megapascals, so I'm just going to do 20 divided by 3 times 10 to the negative 2, and I'll get 670 megapascals. And for 4b, we've got a fishing line, same fishing line that's 2 meters long, and calculate the extension when the strain is 3 times 10 to the negative 2. So our equation for strain is the change in length divided by the length, or sometimes we write it as the extension over the length. We are calculating the extension this time, so that would be strain times the length. So we're going to do 2 times 3 times 10 to the negative 2, and we should get the extension as 0.06 meters, because that's what our original length was in. Question 4c, we've got an area of our fishing line and the breaking stress is 25 megapascals. Calculate the maximum force. So our equation for stress is force divided by area, and we're going to rearrange that to get the force. So we're going to do our stress times our area. So we're going to do 1.25 times 10 to the negative 5 times 25 times 10 to the 6, and that should give us a final maximum tensile force of 312.5 newtons, or 310 newtons to two significant figures. Question 4d wants us to use the answers we've got so far to draw a graph, so I've pulled out the important information at the bottom. So the first thing that we know is the stress at the limit of Hooke's law was 20 megapascals, and we did work out the strain there as well, which was 3 times 10 to the 2, So I'm going to do a little cross on our graph there. So up until then, we know that it obeys Hooke's law. So that is going to be a straight line going through the origin. After that, it's going to curve and it's going to eventually break at 25. So I'm going to draw a curve from that point until 25. It's going to start going mostly straight and then it's going to curve off and then it's going to end at 25. Question 5a has a garden swing made of nickel and copper wire. A girl of mass 40 sits on a swing of mass 1 and she's in the middle at equilibrium. First thing we need to do is calculate the tension in each wire. So if we have a think, we've got her weight coming down, which is mass times gravity, and that's going to be equivalent to the tension from both of these. So we're going to add them up. So for our equilibrium equation, we've got 2t going up is going to be equal to the weight going down. So it's going to be 40 plus 1, because she's 40 and the swing is 1, and we're going to times that by 9.81 for gravity. And if we rearrange that, we get tension is equal to 201.105, or roughly tension is 200 newtons. Nickel has a Young's modulus of 1.7 times 10 to the 11, and the stress in the wire is 7.1 times 10 to the 7. Calculate the strain as she sits on the seat. So our equation for the Young's modulus is stress divided by strain, and we need to rearrange this to get strain. So we're going to do our stress, which is 7.1 times 10 to the 7 pascals, divided by our Young's modulus, 1.7 times 10 to the power of 11. We type that into our calculator carefully, making sure we don't forget our times 10 to the power of, and we should get strain is equal to 4.18 times 10 to the negative 4. No unit because it's strain. Question 5c is talking about strain, because we are looking at the extension and we've got the original length. So strain is change in length divided by the length. So we'll rearrange that to get our change length is equal to the strain times the original length. So we're going to do 5 meters times our strain from our previous question, 4.18 times 10 to the negative 4. And that gives our change in length as a very small number indeed, 2.1 times 10 to the negative 3 meters, or 2.1 millimeters. For the last question, the copper wire also has the length of 5 meters before it's attached to the swing. State the strain in the copper wire and explain your answer. So from our previous question, the strain in the nickel wire was 4.8 times 10 to the negative 4. Therefore, the strain in the copper wire is the same. That's because our seat is horizontal. Therefore, the wires must have extended the same amount to make them the same length at the end, or she wouldn't be sitting straight on her swing.